Welcome back. In this lesson, we're going to look at how scientists use the scientific method as they plan their investigations and their experiments. We're also going to look at how that they gather data in a whole lot of different ways, and that this data is necessary in order to understand what it is that you're studying. We're going to look at the parts of a good study. We're going to look at the independent variable. So the variable is just one small part that can be isolated. So the independent variable is something that you would change. Then the dependent would change based upon what your changes are. Then the control also is something that you're comparing your results to, something that has not changed at all, but that you could see whether there's been, it's a comparison. We're going to look at how graphs and tables are used to communicate data, and also the SI units, which are the units of length and mass, etc., that everyone agrees to use whenever writing a paper. Also, we're going to look at scientific notation, which expresses very, very large numbers and very small numbers. So let's look at this. We're going to begin with the scientific method. And the scientific method is not a specific steps that you take to do a particular experiment, but it's a general template for how you conduct any experiment. So anything that you would have a question about, you make some observations and you have a question. And then the first thing you would do is find out all the information about that question that you can. So you go to the journals, you go to the books that people have found, and you may just have stumbled onto something someone already knows. You just didn't know it. So if that's true, great, you've gotten your answer. If not, you may have to conduct your own set of experiments, and the way you would begin is by an explanation that you simply just come up with. I believe that blank. I believe that all dogs are white. So you make a bold statement, and you're trying to make a statement that can be disproved. So if I were to see a dog or two dogs or five dogs and they were all white, that wouldn't prove that I was right. It would support my hypothesis but not prove it. But if I saw even one dog that was not white, that would disprove. So you're actually trying to be proven wrong. And so that's what's happened. You have your hypothesis, and then you test your hypothesis with a set of experiments, and one or many experiments, and you're testing one little thing at a time that we'll look at. That's called variables. And then you simply tweak and add one experiment to another, so you actually have a series of experiments. So some of the experiments that you have are qualitative, so that they don't involve numbers. They're not measurements. They are descriptions. They are the gorilla looked nervous today, or something like that, or he took all the bananas. So that would be a qualitative type of data. Quantitative is he ate this many pounds of bananas. That would be something that you would write down that's measurable, that's quantitative. And then you're looking at one changeable factor at a time. You want to know what causes what. What is the cause of something else? So you're looking at one little factor at a time. Everything else remains the same, and then that factor is called a variable. Now, you have several kinds of variables. The independent variable is one that's changed by the experimenter. So if I change the amount of time that the plant has to grow, I could see a difference in height. Or if I change the diet that the guinea pig is eating, it might change the weight. Okay, so the independent variable is something that you're changing. Dependent variable is based upon what you change. So something that changes based on what you change. If I change the amount of food, the weight goes up. So the weight would be the dependent variable. The independent variable would be what I change, the amount of that. The control is something that's not changed, and you're using that as a comparison. So you might want if you're testing a fertilizer, have a plant that doesn't have any fertilizer in it that's growing. Then as you test yours, you're comparing it to the one that doesn't have any. So you're comparing it to its control. So your investigation is collecting data. You're watching, you're observing, you're collecting data, and then you simply build one little investigation on top of another, and that's a series of investigations. When you analyze the data, you're basically saying, what does this mean? What does it suggest? Does it suggest that what you eat is based upon how much you weigh? Are you actually claiming that those two things are related or not? Okay, you're analyzing it, and then you are making some conclusions. Your measurements in any type of an experiment needs to be in the SI units. SI is a French word. It just means International System of Units. Everybody in the world's agreed that if you write a paper, you're going to use the same. So meter rather than foot, kilogram instead of pound. These are the SI units. And it's a metric unit, so it's based in 10, and it's very specific. Everyone has basically agreed on them-ish. The SI unit of mass is the kilogram, and we're going to see that a kilogram is about 2 pounds, 2.2 pounds per kilogram. Weight is the Newton. Now, in the British system, we would use a pound also for a weight and mass, but weight is the gravitational pull on a mass. So the bigger the planet you're on, the more it's pulling you, so your weight would be the same. So the picture here, you've got a 2 kilogram mass. On Earth, it would be 19 newtons. On the moon, it would be only 3. Okay, so it's the same amount of material, whether you're on the moon or on the Earth, but the gravitational pull is going to be different. So the weight is actually different than the mass. The area and volume, if you are going to do an area, it's going to be length times width. If you're going to measure volume, it's length times width times height. And density is the amount of mass in a unit of volume. So you take whatever the volume is and divide it into whatever the mass is. Time is the second. Okay, so that will always be the second. So even if something takes a long time, you would record your units in seconds. Temperature uses the Kelvin, and the Kelvin is one of the Celsius temperatures. So it's based on the freezing point of water is 0, the boiling point of water is 100, and then there's 100 degrees between freezing and boiling of water. Kelvin takes that all the way down to absolute 0, which is the idea that there's no movement at all, even in a molecule. So there's completely no energy at all. That would be Kelvin. So finally, we're going to look at scientific notation. And scientific notation is when you want to express a very big number or a very small number. You're going to express it in units of 10. So 10 to the 1 is 10. So if you want to say 70, you would say 7 times 10 to the 1. So 7 times 10 is 70. So all numbers are going to be between 1 and 10, so like 7 times 10 to the 1. Or in the case of this example, 4.1 times 10 to the 4. So 10 to the 4 is 10 times 10 times 10 times 10. So the exponent is how many times 10 is multiplied by itself, multiplied by the coefficient, 4.1. That means you're going to have 41000. So 41,000. That would be how you do something large. You can also do something very small, something less than 1. So a decimal like 0.0001. Okay, you would count the zeros over, and that would be negative exponents. So negative exponents are going to be less than 1. Positive exponents are going to be greater than 10, 100, or 1,000, something like that.